North America. Towering mountains crown a landscape of astonishing diversity. Home to over 500 million people. Its great cities are as individual as the landscape around them. But how was North America made? What forces created its features? What gave it its distinctive shape? This is the extraordinary story of the forging of Earth's oldest continent, the birth of North America. The Earth from space. A unique perspective. It helps us understand the forces that continue to shape our world. Earth has 7 continents. This is the story of one of them. North America takes up 16% of our planet's total landmass, more than Europe and the Middle East combined. It is home to Yellowstone National Park, the Grand Canyon, Mount St. Helens, and the largest group of freshwater lakes on the planet, the Great Lakes. It's also home to the world's oldest rocks. Rocks that have helped to reveal our planet's dramatic history and unravel the secrets of the birth of America.
The cool thing about this planet is that with the eyeballs of somebody who's thinking about rocks, you can look at a layer of rock and say, hey, that's not a layer of rock. That's an ancient swamp, or that's an ancient sand dune.
To decipher North America's past, geologists must first find its origin. In Canada's Northwest Territories, some 200 miles from the nearest city, this rock outcrop near the Acasta River is the first chapter in the story of the birth of a continent. Dr. Wouter Bleeker is working here to pinpoint just how old America really is.
Here at Acasta, we find the oldest continental crust, actual rocks you can stand on. So we basically see the initiation of continental growth here. This is where it starts.
The birth of America is set in motion 4.6 billion years ago as our sun explodes into life. Gas and debris hurtle around it, and eventually 8 planets emerge from the vortex. At more than 12,000 degrees Fahrenheit, one of these newly formed planets appears nothing more than a ball of boiling lava. Earth is a primeval hell. The heaviest elements, like nickel and iron, sink down toward the center of the Earth and form its core. The lighter elements, including oxygen and silicon, rise toward the surface and form oceans of molten rock. Slowly, the Earth's surface cools. The lava solidifies and forms patches of crust. As this crust grows, it gets heavy and sinks back down into the mantle. Deep below the surface, it remelts, and the lighter elements rise up again, eventually forming granitic lava. Granite is less dense than other rocks in the mantle. It floats on the surface. As it solidifies, it forms rafts of land.
Think of it as the scum on a pot of soup. If you boil that soup long enough, that scum will nicely separate and float on top of the soup. And that is what continental crust is. It's basically the scum of the Earth.
Here at Acasta, this scum is actually a granitic rock called tonalite.
Tonalites are important because they are the first materials that actually make stable continental crust.
All continents contain chunks of tonalites that date back over 500 million years. These form rafts of continental crust called cratons. North America is made up of at least 6 of them. For researchers to date the birth of North America, they must find the earliest craton. And to do that, they have to date tonalite from all over the continent. It's a complex process. They look for microscopic evidence created as the rock was formed. Telltale mineral crystals, tough enough to survive over eons. One of the toughest minerals of them all is zircon. Zircon contains uranium-238, an unstable radioactive isotope. Scientists know that this isotope decays, gradually turning into lead. Importantly, they also know exactly how long this process takes. Imagine that the top half of this hourglass is uranium-238 and the bottom is lead. Over 4.46 billion years, half of the sand representing uranium will drop into the compartment representing lead. That's uranium-238's rate of decay, its half-life. By measuring the amount of lead and uranium isotopes in the zircons from the Acasta tonalite, scientists can pinpoint the rock's age and figure out how old this part of North America is. The tonalite found near the Acasta River in Canada's Northwest Territory is 4.03 billion years old.
This is the oldest rock in the North American continent at this point in time, right here at Acasta, within the core of the Slave Craton.
These tonalites predate most other rocks by billions of years. They are the oldest rocks ever discovered. The core of the Slave Craton in North America contains the oldest surviving landmass on Earth. The next challenge is to figure out what embryonic North America might have looked like. Professor Ron Blakey is an expert in continental mapping at the University of Northern Arizona.
When the early continents formed some 4 billion years ago, they were probably scattered about the surface of the Earth. But this far back, we would just be completely speculating on what the position of the continents would be.
This is our planet today. 7 distinct continents, all surrounded by water. But take away the oceans, and we see that a hard outer shell, or crust, covers the Earth's surface. The oldest and thickest crusts form our continents. That's around 40% of Earth's skin. The rest is underwater, oceanic crust. Oceanic crust forms a thin layer at the top of the Earth's mantle, an 1,800-mile thick layer of superheated molten rock, magma. Heat escaping from the center of the Earth creates convection currents in the mantle. It's believed that this slow boiling motion breaks the crust up into pieces called tectonic plates. In some places, magma from the mantle escapes through the gaps between plates. As it rises and solidifies, it forms new oceanic crust and forces the plates apart. In other places, the mantle drags oceanic crust down, consuming it. As a result, the Earth's crust is constantly moving, traveling about 30 miles every million years. Ohio University professor Damian Nance specializes in plate tectonics.
We create, if you like, a conveyor belt, and continents are carried by these conveyor belts, much like suitcases on an airport conveyor belt.
Starting some 4 billion years ago, Earth's churning interior and a cooling of its surface creates and moves these rafts of land. Cratons collide and form continents. Some of these merge, forming supercontinents. Valbara, Rodinia, Laurussia, and Gondwana. 3.5 billion years after the oldest surviving continental crust forms, Gondwana moves slowly north from the South Pole, breaking up into smaller pieces. Eventually, these pieces recombine with others, forming a landmass of incredible size. From this, North America will eventually emerge. Over billions of years, the dynamic movement of Earth's crust has shaped and moved entire continents. When these landmasses collide, they produce mountains. These are the Appalachians, the oldest surviving mountain range on the continent. Today, they stretch nearly 2,000 miles southwest from Newfoundland to central Alabama. But when they first appeared over 270 million years ago, North America still did not exist. These mountains crowned a supercontinent called Pangaea.
When they were at their maximum height, they would have been perhaps the most profound mountain range existing on the planet.
In a road cut in the Appalachian foothills, Ohio University professor of geological sciences, Damian Nance, examines the geology exposed in the Appalachians today.
What may look a rather unimpressive wall of rock to the casual eye has proven to be a geologic Rosetta Stone in this part of the Appalachians, and it records the very first collisional event in the building of the Appalachians.
These belts of folded rocks are the surviving record of 3 titanic collisions that created the mountains. Billions of years after the creation of the Acasta tonalite, 2 ancient continents begin to collide. As these 2 continents close in on each other, the ocean floor is pushed down underneath what will become Africa. Gradually, the ocean is consumed. Huge sections of the seafloor are dumped on the edge of the continent, creating ridges and valleys. As the continents continue their inexorable journey, island landmasses are compressed between the 2. The debris accumulates, now on dry land. The continental collision forces the debris further upward, driving the Appalachian Mountains higher. It's the geological equivalent of a car crash.
If you imagine a wreck between a truck and a much smaller car, the first thing that happens when the 2 hit each other is a collision between the front of the 2 vehicles. And you can think of that as the first collisional episode in the Appalachians. The next thing that happens is the truck hits a windshield, and that, if you like, is a second collisional event in the Appalachians. And finally, the car disappears under the truck, and that, if you like, is the climactic collision, the one that produced the final Appalachian and brought the whole process then to a close.
This mountain building process involves hundreds of thousands of cubic miles of rock. It's thought the Appalachians originally rose higher than the present-day Himalayas. Today, they are a shadow of their former selves, cut down to size by another powerful geological process, erosion.
One of the great lessons of geology is that mountains are ephemeral. They go up and they go away. They're pushed up by forces inside the Earth, and they're eroded away by erosion. And erosion can happen pretty fast. I mean, if you're merely to erode 1 millimeter a year, 1,000,000 years is enough time to get rid of a kilometer of mountain.
The mighty Appalachians were tamed by another powerful enemy, water. When water freezes, it expands in volume by as much as 8%. Here, a bottle of water rapidly freezes. The ice expands, and the bottle cracks. This same action applies to rocks. Water freezing in cracks breaks them apart. When temperatures rise, the ice melts and washes away the debris. Wind and rain add to the process, and over eons, they have the power to utterly transform the landscape.
Erosion can do incredible damage to a mountain range, and we can see that in the modern Appalachians. The modern Appalachians are simply the remnants of this once vast and very high mountain range.
Today, Pangaea's eroded mountains are in North America. How they came to be here is the next step in the story of the continent.
Continents trap heat. Continents act a little bit like a book on an electric blanket. If you put a book on an electric blanket, it gets hot.
The book acts as an insulator, trapping heat underneath it.
Continents do the same thing with heat generated in the Earth's interior. And so if you put a very large continental mass together, like Pangaea, heat builds up beneath it.
Pangaea is big. It's nearly as big as all of our 7 continents put together. The temperature builds up underneath the continent and heats it up. As the rock absorbs heat, it arches. Then, at its weakest points, it cracks, including along the line of the Appalachian Range. It's a process called rifting.
Here's North America about 210 million years ago. If we look carefully, we can see some of the rifting between Africa and North America, where the Atlantic Ocean will eventually form. Just for reference, New York is right here. So the distance from New York to West Africa wasn't even as great as the distance from New York to Chicago.
As Pangaea cracks, it creates long, thin valleys. These elongated depressions fill with sediment washed down from surrounding highlands. Today, we call one of these the Newark Basin of Pennsylvania, New York, and New Jersey. This sediment, now solidified, has been quarried. Today, you can see it on the streets of New York City every time you look at a brownstone. 230 million years ago, the rifting between North America and Africa creates a new ocean, the Atlantic. As the two landmasses continue to pull apart, water floods the widening gap. The continental landmass we call North America is created, nearly 4 billion years after the first land formed. Its shape and features look different from the continent we know today. Other geological processes will change them. America is constructed by plate movement, but it is shaped by fire, ice, and water. 150 million years ago, Pangaea's disintegration begins a new phase in North America's evolution. Some of the continent we recognize today is submerged underwater. Millions of years after Pangaea splits, A shallow sea stretches across the interior of the North American continent. It's called the Western Interior Seaway. It bisects North America from the Arctic Ocean to the Gulf of Mexico. It is the hunting ground of mighty carnivorous reptiles, mosasaurs and plesiosaurs.
And you think, wow, that's amazing. A sea was on this continent. But it's not that amazing. A continent like North America is quite large. Yet the highest point in North America is Mount McKinley, which is a mere 4 or 5 miles tall. So you have a continent that's 4,000 miles wide, and the highest point is 4 miles. The continent's effectively flat as a board. And of course, it's wrapped onto the Earth. So if the continent flexes a little bit, flexes down, the sea can come onto the continent. Flexes up, the sea goes off the continent.
It's a process called uplift. 70 million years ago, a giant uplift forces the inland seas outward, emptying the continent. The retreating seas leave a rich mix of layered sediments in their wake. In time, this seabed will become America's Great Plains, an immense sweep of country reaching from Mexico, across Texas, up to Montana, and into Canada. Denver Museum of Science and Nature's curator, Kirk Johnson, specializes in the region.
For 20 million years, this area wasn't a mile high. It was 600 feet below the surface of the salty sea. Just go dig a hole in the pure shale and you'll find the teeth of 50-foot-long marine reptiles and giant fossil fish and ammonites and meter-long clams, a whole host of things that really show you that there was a sea right here.
Uplift drains the sea away from the interior plains. Further west, the same uplift triggers a different effect. The results are still visible today.
The entire western interior of North America was flat as a board. Then, about 69 million years ago, the Rocky Mountains pushed up.
Most mountain belts are created on the margin of colliding plates. But the Colorado Rockies formed more than 600 miles away from the edge of the Pacific Plate. Some other force must have pushed them up.
The subducting plate off the west coast of North America, instead of going in and diving down and creating volcanoes right along the margin of North America, went in shallow. Like a spatula under a pizza.
Cracks in the crust allow granitic magma to escape the mantle. It rises to the surface and creates volcanoes. Today, there are 262 volcanic fields in North America. The majority of them have had little impact on the surface of the continent. There is one exception. It's called a supervolcano. Supervolcanoes leave enormous scars on the landscape, scars that are visible today. This is a satellite view of the Snake River Plain. It's 400 miles long, a broad, flat depression that covers 1/4 of the state of Idaho. It's best known for its fertile agricultural land, home of the famous Idaho potatoes. The land here contains a record of the North American plate's gradual movement over a stationary hotspot in the Earth's mantle. This hotspot produces a place on the Earth's surface that experiences active volcanism for long periods. Below the crust, abnormally hot mantle material wells upward. As North America drifts across this hotspot, it leaves unmistakable evidence of each eruption on the surface of the Earth. Today, the hotspot is directly under Yellowstone National Park. Eventually, the park's boundaries will pass over it. But for now, Yellowstone is the largest volcanic system in North America. Hank Hessler is the Yellowstone National Park geologist.
Trying to imagine what the catastrophic eruptions look like is a challenge. No human has ever witnessed these type of eruptions.
But humans have recorded devastating eruptions in the past. May 18th, 1980, Washington State. Mount St. Helens erupts with a total force of 24 megatons. That's almost 1,600 times as powerful as the bomb that destroyed Hiroshima. But compared to an eruption at Yellowstone 2 million years ago, Mount St. Helens is small change. Today, the caldera of the last eruption of this supervolcano forms the heart of Yellowstone National Park. Calderas appear when the magma chamber beneath the volcano empties after a large eruption. Fractures form around the edge of the chamber. They serve as vents, and as the magma chamber empties, the center of the volcano collapses.
So much magma has erupted forcefully, forming volcanic ash, that the ground has actually subsided into a large hole. And this particular hole is about 45 miles long by 35 miles across.
Yellowstone scientists have calculated that the eruption 2 million years ago ejected 588 cubic miles of volcanic material into the stratosphere.
To put this in comparison, this is about 6,000 times larger than Mount St. Helens. What does 6,000 times larger than something mean? Well, many of us have spent $1,000 in our lives. 6,000 times larger than $1,000 is $6 million. And not many of us have spent $6 million in our life.
A supervolcano belches millions of tons of sulfurous gases and ash particles into the atmosphere. This volcanic debris reflects the sun's rays, decreasing the amount of sunlight reaching the surface of the Earth, often triggering what's called a volcanic winter. Volcanic winters can drop global temperature by up to 9 degrees. Plummeting temperatures have also shaped modern North America. During much of the last billion years, the Earth has had no permanent ice. But cooling temperatures have occasionally helped cover much of the globe with immense ice sheets. These are ice ages. 200,000 years after an eruption at Yellowstone, the Earth enters an ice age. Boulder-studded glaciers advance and retreat over much of North America, carving and sculpting the landscape. Hofstra University professor of geology, Charles Magarian, is an expert on glaciation.
These boulders act like tools and actually gouge the Earth's surface and produce gouges and grooves on the orders of feet.
It's like repeatedly dragging a cheese grater over cheese. Boulders embedded in glaciers gouge out grooves on the surface of the continent over and over again.
But it's the final polish of the Earth's surface and the position of streams and creeks and valleys that was the product of glaciation.
But the glaciers have another important effect. At the peak of the last ice age, so much water is trapped as ice on land that sea levels drop by as much as 450 feet. Huge new tracts of land are exposed. Today, you can stroll to the shoreline from New York's boardwalk in just a few minutes. During the last ice age, it would take days.
During glacial periods, when sea level was down 50 to 100 meters, the walk was about 200 miles to get to the shoreline because the entire continental shelf of eastern North America was exposed during the last glacial episode.
The Ice Age exposes so much land that America's coastline looks very different than it does today. Florida is around twice as wide as it is now. 300,000 years ago, the outline of North America as we know it today is trapped in ice. It's only when the glaciers finally melt that the true shape of the continent will emerge. 300,000 years ago, glaciers from the last great ice age are sculpting North America. Giant boulder-studded ice sheets gouge large chunks out of the earth. They create depressions in the landscape. When the ice melts, it pools.
The most obvious effects of glacial meltback is the Great Lakes of the upper part of the United States, where enormous tracts of terrain that have been sculpted by glacial ice were later filled in by the meltback of glacial ice sheets.
North America's Great Lakes cover more than 94,000 square miles. They hold enough water to submerge the contiguous 48 states under 9.5 feet of water. They are the largest group of freshwater lakes on Earth. So big, they are often described as inland seas. They emerged toward the end of the last ice age, when ice sheets many times the size of Texas recede. As ice sheets melt, water fills depressions in the landscape, creating millions of lakes. This is the most unique. It is Utah's Great Salt Lake. It's actually just a small remnant of a much larger ancient one. Lake Bonneville covered almost 20,000 square miles. Salt Lake City is built on its bed. The ancient lake existed from about 30 to 14,000 years ago. At more than 1,000 feet deep, Lake Bonneville was deeper than Lake Michigan. Professor Marjorie Chan of the University of Utah stands above Salt Lake City on the ancient shoreline of the Bonneville Lake. She's been studying it for 6 years.
We're on the ancient shoreline of Lake Bonneville, and about 15,000 years ago, at this elevation of 5,100 feet, the whole area and valley behind me would have been covered by a deep lake. Antelope Island and Stansbury Island would have been surrounded by fresh water, maybe with even fish, and perhaps even my toes would be in the water at the shores of Lake Bonneville.
Fed by meltwater from retreating glaciers, the level of Lake Bonneville gradually rose. 15,500 years ago, the water reaches an elevation of about 5,000 feet, the lowest natural outlet for the basin. At Idaho's Red Rock Pass, the lake begins to spill over. The outflow of water begins to cut down into the rocks. Red Rock Pass weakens and then collapses, unplugging the lake and causing a catastrophic flood. 15 million cubic feet of water gush out of the lake every second, about 150 times greater than the flow at Niagara Falls.
The amount of water that was rushing out would be the equivalent to, more than that goes through the Amazon River, just huge amounts of water. And this is what we call the Great Flood.
In about a year, the lake's level drops by almost 400 feet, releasing 380 cubic miles of water onto the Snake River Plain. The lake only stops emptying when the water level drops below the outlet at Red Rock Pass. The remaining water slowly begins to evaporate, leaving behind salt crystals. Over thousands of years, almost all of the lake disappears. Large salt flats mark its boundaries. Today, the Great Salt Lake is all that remains. The retreating glaciers of the last great ice age leave their mark all over North America. There's evidence in the most unexpected places. New York, America's famous city. Most of us associate it with skyscrapers, not glaciers. But New York's frozen geological past has shaped the city. Just 20,000 years ago, Manhattan and the Bronx were scoured by great plates of ice. Look past the joggers and workers enjoying their lunch break, and you can find plenty of evidence of glacial movement, even in Central Park. Dr. Charles Magarian can spot the signs a mile away.
Picture a thick ice sheet, an ice sheet that is perhaps a mile thick. Think about the mass at the base of a mile-thick sheet of ice, enormous pressures. And these enormous pressures literally pulverize rock.
The rock formations in Central Park bear the scars of this pummeling.
We're standing here right in the center of the large exposure of rock, much of which has been removed by a glacier.
20,000 years ago, New York is covered by a sheet of ice 5,000 feet thick.
And you can picture how a 1 mile thick sheet of ice with huge boulders embedded in the base of the ice would have created this groove.
The abrasive cycle of glacial advance and retreat even affects the city's design.
It's amazing, but even the skyline of New York is dictated by geology. Turns out that tall buildings, which are the hallmark of New York City, must be rooted in solid rock. If you look at Manhattan, you recognize that the building heights actually oscillate from high buildings to low buildings back to high buildings again. Why? Because in that area, there's a very deep valley that's been sculpted by glacial ice and then backfilled with glacial sediment. Well, you just simply cannot build tall buildings in soft sediment. So the building height change in New York City is actually showing what the underlying geology is.
North America's glacial period finally ends about 8,000 years ago. It has shaped the coastline of the continent and applied the finishing touches to the landscape. Glaciation has molded our cities and left behind great lakes, plains, and mountains. The continent we know today has finally arrived. This is continental North America. In the future, plate movement will rip the continent apart, just as it has time and again throughout its long past. It's happening today, right under our feet. This is the San Andreas Fault. It runs roughly 800 miles through California. It's the main boundary between the Pacific and North American tectonic plates. These two plates are moving in opposite directions to each other. The Pacific plate is moving northwest relative to the North American plate. California is being ripped apart 2 inches a year. At this rate, 1 million years from now, California will separate from North America and become an island state like Hawaii. But that's not all. If we plot the projected movement of the Earth's plates over the next tens of millions of years, the face of the whole continent becomes unrecognizable. 50 million years from now, the Atlantic Ocean has widened. It has pushed New York away from Africa, moving the continent across Yellowstone's hotspot. Minnesota now sits on top of the supervolcano. 100 million years from now, California's Napa Valley and San Francisco Bay Area have become Alaskan mountains. The Atlantic Ocean continues to widen. A subduction zone forms along its western shoreline. This zone will consume the Atlantic Ocean and set North America on a collision course with Europe and Africa. 200 million years from now, America's eastern seaboard no longer exists. North America and Europe collide to create a new supercontinent. Today's New York is now in the middle of a mountain range, once again at the center of a huge landmass, just as it was 500 million years ago. This may be our continent's future, but on a timescale that far outstrips our lifetimes. There are other changes, however, that mankind will witness. In the coming centuries, the North American continent may be a very different place. Much of Florida is underwater. The Big Apple is a modern-day Atlantis. It's an apocalyptic vision of North America's future. But it's us that's making it happen. For the first time in Earth's long history, the natural processes that forged the planet's continents are being influenced by man.
Humans are very, very powerful geologic agents. Look at the farm fields that stretch over hundreds of thousands and millions of acres. Look at the expansion of cities over many tens of square miles that have completely changed the landscape.
By the end of this century, the population of the United States alone is set to double. To accommodate our ever-growing population, we're building new cities. Industrialization, our use of fossil fuels, and our continuing love affair with the automobile has sent carbon dioxide levels in the atmosphere soaring. Carbon dioxide traps heat inside Earth's atmosphere, increasing the greenhouse effect. The ice caps are melting, and sea levels are beginning to rise. Jeremy Weiss is a global warming expert at the University of Arizona. He paints a gloomy picture of the future of North America.
With global warming, there are certainly going to be winners and losers. The losers, however, are going to be far outnumbering the winners.
Sea level rise associated with global warming will literally shrink North America.
The shape of North America could change significantly, especially along the Gulf coasts and Atlantic coasts of the United States. For example, the states of Louisiana, Florida, and North Carolina will see the greatest effects as far as loss of land to sea level rise.
Minimizing or reversing these trends requires urgent action. In the short term, the next 100 or so years, the shape and character of continental North America will change. How dramatically is up to us. In the long term, we make no difference to nature's billion-year-old processes of growth and destruction. These are impossible to control. The awesome forces that created North America are still at work. We won't be around to see the results of these changes. But perhaps other generations will map their new continent and reveal evidence of our time. just as we have unearthed the story of North America so far.